Bun găsit la emisiunea Știință și Cunoaștere. Știința mediului face parte din acele forme de cunoaștere care au rolul de a ne face să devenim mai conștienți de noi înșine prin înțelegerea rolului și locului pe care îl ocupăm în cadrul biosferei. Între cunoașterea de sine și cunoașterea naturii se formează o legătură bionivocă. Aceasta înseamnă că pe măsură ce devenim tot mai conștienți de noi înșine, devenim totodată tot mai conștienți de integrarea noastră în mediul natural. Dar putem explora această idee și din celălalt sens, astfel că pe măsură ce devenim tot mai conștienți de mecanismele uimitoare ale naturii, ele ne ajută să aflăm mai multe despre noi înșine. Expunerea profesorului canadian Tim Ball ne provoacă și ne îndeamnă să facem un asemenea exercițiu de cunoaștere. În acest context, lecțiile domnului profesor sunt multidisciplinare, acoperind o gamă largă de discipline. În timp ce ascultam cu fascinație discursul său, am avut sentimentul că chiar asist la emergența unei noi științe, ce nu a fost niciodată divizată pe sute de ramuri și subramuri cum avem în prezent. Probabil unii dintre dumneavoastră vă amintiți acel serial documentar numit Conexiuni, realizat de James Burke. Este cea mai bună comparație pe care o pot face cu discursul indivizibil al profesorului Tim Ball. Am fost șocat să aflu, de exemplu, faptul că un detaliu mic de pe o pictură medievală releva grosimea gheții unui fluviu din Anglia în perioada Micii Ere Glaciare, în timp ce alte picturi dezvăluiau elemente din care s-a estimat gradul de acoperire noroasă. În cel de-al treilea episod al acestei miniserii rezervată schimbărilor climatice, vom discuta despre o descoperire esențială din domeniul astrofizicii, care a elucidat misterul apariției norilor, și anume faptul că Pământul este în permanență bombardat de radiații cosmice. Și apoi veți afla detalii uimitoare legate de clima din perioada ultimei răciri globale, desprinse, cum spuneam, din picturile medievale europene. Știați faptul că aurorele boreale sunt indicatori climatici? În perioada Micii Glaciațiuni acestea au fost aproape inexistente. Vom vorbi despre elemente ce țin de științele agricole și modul în care apa de ploaie pătrunde în sol, iar spre final veți afla un secret legat de modul în care puteți construi și exploata o fântână, astfel încât să aibă apă în permanență sute de ani. Fiți alături de noi la acest eveniment special la Știință și Cunoaștere împreună cu profesorul Tim Ball. Dear Professor Tim Ball, welcome to our Science and Knowledge TV program in Romania for part 3 of our second interview.
Thank you. It's a wonderful opportunity.
It is a real pleasure to discuss wonderful topics with you again.
Thank you. It's a fascinating world, just an amazing world.
The next topic, which continues our discussion, is Sven Marx's cosmic theory and cloud-covered depictions in Little Ice Age art. Please explain this long paper and let's follow the drawings on the web page.
Okay. One of the things that, and we need to go to what people understand about climate from the United Nations Intergovernmental Panel on Climate Change. They only look at human causes of climate change because they wanted to focus on CO2. The problem is that you cannot determine what effect humans and their CO2 is having unless you understand all of natural climate change and all of the mechanisms involved. One of the things that we know is very important, and in fact it's a major failure in their computer models of climate, are clouds. What effect they have upon the weather and the climate. And no matter where you live, you know how when the clouds come over, the sunlight gets blocked and the temperature is decreased. But also sometimes at night, if you've got cloud cover, the heat doesn't escape from the earth and the temperature doesn't drop as much overnight. So clouds are absolutely critical to understanding what's going on with climate change. But we really don't fully understand. Now, for example, in one of the last programs, I talked about the little particles, condensation nuclei, that is particles in the atmosphere essential for water to change from a gas to a liquid. The liquid that's created is called water droplets. Those are minute, microscopic in size, but because there are so many of them in a cloud, you can see them as the cloud. And but we knew for a long time, hundreds of years, that there weren't enough nuclei, that is particles in the atmosphere, to explain all of the cloud cover that we had. Now, the two major sources of these nuclei are dust from the Earth's surface, mostly clay particles, which are the smallest particles of soil that you can find, and the other is salt particles from the ocean. Those are the major condensation nuclei, but there weren't enough of those in the atmosphere to explain all the cloud cover that we have. And by the way, just as sort of an interest, rain or snow, precipitation, only comes out of 1% of all the clouds that are ever formed. So the actual formation of rain and snow is a very, very complex process. But anyway, there was this problem of the cloud cover and how it varied. But there was another problem that occurred. We knew that when there were sunspots, the global temperature, when there were lots of them, the global temperature was warm. When there were few of them, the global temperature was cool.
Yes, and about that, can you tell us about figure 1 from the article?
Sure.
The solar climate relationship.
Yes. Now what we knew was that okay, so we're looking at
But first, please open the page on Sven Marx cosmic theory.
What we knew was that there were sunspots, and they seem to relate to temperature. That is, that when there were lots of sunspots, the Earth was warm. When there were very few, the Earth was cold. But one of the dangers in science, and well, in society in general, but especially in science, is that that's what we call a correlation. So you've got sunspot numbers varying and the global temperature varying, but you can't say that they are cause and effect, so that you cannot say that the sunspot numbers are causing the temperature to change unless you know what the mechanism is. So what is the cause of this change? I used to tease my students about this, that the kinds of dangers of correlations, say that Diet Coke causes obesity, because the facts are that more fat people drink Diet Coke than anybody else. Okay, so you then conclude that the Diet Coke is causing the obesity. And of course, we know that's not true, but that's an example of the dangers of having facts and drawing conclusions about them without knowing the proper science and the method involved. And that's very essential to what we're talking about here. So we had this problem, and quite rightly, the Intergovernmental Panel on Climate Change said, okay, well, we know there's a relationship, a correlation, but because we don't know the mechanism, we can't talk about it. Well, starting in 1991, a paper was published suggesting the relationship between changing sunspot numbers and global temperature by Christensen and Larson. This is 1991. And what they found was the length of the sunspot cycle varied with the number of sunspots and the temperature. That was the first indication of some, but still not a mechanism, still just a correlation. Well, then around 2000, Sven Marx, a researcher, discovered that what was happening was that the Earth is bombarded with cosmic radiation. In fact, the whole of the universe is full of cosmic radiation. It comes from exploding stars in the universe, from galaxies. Jupiter is a major emitter of radio waves and energies. So nobody thought this cosmic radiation was of any great consequence until Sven Marx noticed that there was a correlation between cosmic radiation and cloud cover on the Earth. And he then said, well, how is this happening? Well, what he discovered was the amount of cosmic radiation reaching the Earth is controlled by the magnetic field of the sun. So as the strength of the sun's magnetic field varied, because of course it's a variable star, it's not constant. Everything's always changing in nature. And so as the strength of the sun's magnetic field varied, it controlled the amount of cosmic radiation coming to the Earth. And you can see that in figure 2 in the article. You can see that the cosmic radiation from exploded stars coming down to the Earth's atmosphere, but the amount is determined by the sun's magnetic field. Now, the sun's magnetic field, its strength varies at the same time as changes within the sun itself. And those changes within the sun itself also create the sunspots. So the sunspots themselves were not the cause of the temperature change. It was just that they were evident changes in the sun that were occurring at the same time as the changes in the magnetism. So as the sunspot numbers varied, then the sun's magnetic field strength varied, and that controlled how much of this cosmic radiation could reach the Earth's atmosphere. And you see that at the top of figure 2. Now, as those particles, those cosmic ray particles, pass through the atmosphere, in the lower atmosphere, they are changed by a chemical physical process into condensation nuclei. In other words, they become particles around which water, the gas, can condense to form water droplets. So when you plot the amount of sunspot activity against the low cloud cover, as the cosmic radiation varies, so the low cloud cover varies. Now that affects the temperature of the Earth very directly, because it's just like putting up a screen in a greenhouse. So you're controlling the amount of sunlight that's getting to the Earth's surface. That, of course, then controls global temperature. And that's what Sven Marx's cosmic effect was all about. Now, they didn't want to accept this because, of course, they wanted to say, oh, no, it's all caused by CO2. The sun has nothing to do with this. Well, they tested Sven Marx's cosmic ray theory at nuclear collider in CERN in Switzerland. You know, where they bombard atoms with high energy? It's called CERN. It's the,
Yes, we have a team of experts in Cluj who also works on this project.
Okay, well, they tested to make sure that what Sven Marx was saying, that is that these cosmic rays do become nuclei around which water can form, was true, and that was confirmed about 4 or 5 years ago. And as I said, when you plot the cosmic ray reaching the Earth with low cloud cover, it's a very, very high correlation, like about 97% correlation. So what I did in this particular article was that I took that idea back into the historic record and wanted to see what evidence we had in the historic record. Figure 3 shows you actually a diagram that is very, very important in what's gone on in the corruption of climate science. But that figure appeared in the 1990 IPCC report. It shows the temperature variation for the last 1,000 years in the northern hemisphere. And that's important to understand. On the right-hand side, you can see the modern warming. And of course, what they were saying by 1995, they were saying, well, today the temperature is warmer than it's ever been. This diagram showed that it was warmer 1,000 years ago in the medieval warm period. And by the way, very interesting, if you look at Romanian European history, during that period around 900 to 1100 AD. We talked about it briefly in a previous program because that's when the Vikings, the population exploded because the temperature and the climate improved in Scandinavia. Food supply means a growth of population, and when the population explodes, it usually moves out, migrates. So the Viking people spread out around the northern hemisphere in that medieval warm period, and they arrived in what is now Moscow around 1000 AD. And by the way, we've got very good climate records from that time period from the Russian chronicles. And I worked with a Russian climatologist by the name of Borisenkov, and he was looking at these Russian chronicles, which show changes in the weather and crop productions, because that's what's important to world leaders, the ability to feed people. But what this diagram showed was the medieval warm period 1,000 years ago was warmer than today's temperatures. And of course, that was opposed to what they were claiming. They were saying that because human CO2 has caused more warming, it's warmer now than it's ever been. So this diagram, and we can talk about it a bit later, but there was an email sent by one of the people at the Climatic Research Unit, where the emails were leaked from, to a Professor Deming, who I've known for 30 years. Now, he published an article, and they obviously thought that he was agreeing with them, that CO2 was the problem. And they said, in the email, they said, we have to get rid of the medieval warm period. Okay, in other words, we have to rewrite history. Well, of course, that then became the famous hockey stick that we've talked about. Okay, now, what I wanted to show, because the argument was made that, oh, well, the Little Ice Age, the cold period around 1650, by the way, when there was massive starvation in countries across Europe, it's estimated in 1688 that almost 3/4 of the population of Finland starved to death in one winter. So when we talk about climate and its effect on human populations and food supply, you can see the impact of that. And that, by the way, Christian, is important because, as you know, a lot of us think the world is cooling down, and a colder world is much more difficult for humans and plants and animals. But anyway,
and it lasted 70 years.
Exactly. It lasted 70 years. Exactly. Okay, and then that's what we're looking for now. Anyway, what I wanted to do was to take paintings from the period of the Little Ice Age and to see if they confirmed an increase of cloud cover during that Little Ice Age, which of course would have had the effect upon temperatures. So I took the paintings, Bruegel's paintings. Of course, there was the father, elder Bruegel, the son and the father. They were the first people to really start painting landscapes and painting the lives of ordinary people.
Yes, I'm watching figure 4 and figure 5 right now, but I don't understand some detail on figure 5. All what is seeing there is the river Thames completely frozen.
The river Thames was frozen. In 1683, there was a meter of ice on the Thames River in London, England. And that's a river today that doesn't get any ice at all. So you see how much colder it was during the Little Ice Age. And if you look at that picture closely, on the left of center, you'll see St. Paul's Cathedral. You see the dome of St. Paul's Cathedral. See where the smoke's coming up from the fire in the foreground. And people are on the ice, and they're having what's called an ice fair. So that when the river froze over, they would go out on the ice and have a fair. So people were selling things, and you can see, if you look to the right center, you can see a carriage and 4 horses on the ice.
Yes.
That tells you how thick the ice was. Okay, now the River Thames, ice of that thickness the river started to freeze over around the reign of Elizabeth I, around 1540. So as the world started to cool down from the medieval warm period, the River Thames started to freeze over. And the worst frost year was 1683, which of course was right in the middle of the Little Ice Age. Now, in Europe, of course, Bruegel was painting similar scenes of very cold and snowy conditions in Europe at the same time. And by the way, in that picture by Glaciare, you can also see on the right-hand side, that's Westminster Abbey, which of course is a famous part of London. And then on the left-hand side, in the center, is Lambeth Palace. Those are both still there, but you can see this medieval ice fair. Queen Elizabeth and her court used to skate on the River Thames quite regularly. It was part of their entertainment. The last ice fair, as you see depicted there, occurred around 1840. So as the world came out of the Little Ice Age and warmed up towards the current warm period, then the ice stopped forming. And of course, now if you show people pictures like this, they can't believe that there was that much ice on the Thames River.
But can you tell me how many months of winter England had at that time each year?
The winter, which now lasts about 2 to 3 weeks in London, England, was 3 months. Now, one of the records we've got of that was Charles Dickens, the novelist who wrote famous books, English books. He talked about, in his first 10 years of life living in London, England, it snowed every single winter, and the snow stayed on the ground for 2 to 3 months. As you know, in London, England today, they maybe get snow for a couple of days and it melts and it's gone. So Dickens, and he's writing in the period around 1820. So that's one of the direct measures we've got of the length of time that the snow stayed on the ground. But as you can imagine, for that picture by Glaciare...
Okay, but how many months of winter had other countries like Romania at that time? Because in present days we have 3 months of winter.
It was at least 4 to 5 months of winter at that time. And there is very, very extensive research of the historical record done for Europe by a lot of different climate scientists reconstructing the conditions. One of the best books, called The Little Ice Age, is a book by Jean Grove, Grove. And she documents all of the evidence of the Little Ice Age, how long it lasted, what impact it had. For example, in Scotland, they used to farm up the sides of the valleys, but in the maps of the Middle Ages, and Martin Parry's produced maps of this, they were in the county of Berwickshire, for example, which is a county in England. They were farming about 3/4 of that county in 1000 and 1100 AD. By 1600 AD, they were down to farming only about 1/4. So over half of that county could not produce food anymore. And your listeners might know about something called the Highland clearances in Scotland, where all the people were chased out of the highlands, and the historians say, oh, it was because the landlords didn't want them, they wanted to get rid of them. Wasn't the case at all. What happened was the height up the sides of the mountains that they could farm lowered by about 600 meters. Now that doesn't sound like very much vertically, but when you think about it on a gradient, it means a great deal of land went out of agricultural production. That happened all across Europe. Very large areas of what was previously, because as you know, it's not just the length of the winter that's important, it's the length of the growing season. The frost-free season is critical, and particularly in Europe, where you've got a much greater temperature range. So if you lose even 2 or 3 weeks off of your growing season in the summer, then there are a lot of crops that are simply not going to grow anymore. And in fact, in Scotland, in a period of about 100 years, they went where they were able to grow wheat to where they were not able to grow wheat, or corn as the English call it. And they could not grow corn in Scotland until late in the 19th century as the earth warmed up again. So the impact of that little ice age on European history all across was very, very measurable. And as I say, the Russian chronicles, Borisenkov's work shows that, but particularly Gene Grove's book, The Little Ice Age, shows it. In the United States, exactly the same thing was happening. George Washington, his troops were freezing to death during the Revolutionary War. And so totally different conditions than we're familiar with today, but all part of that natural cycle as depicted in Figure 3.
Now I'm following Neuberger's hypothesis. He studied more than 12,000 paintings.
Yes. Okay. This was an attempt to, because artists paint what they see. Yes, they do some imagination and so on, but what he did was that he took 12,000 paintings from 41 European and American art museums, and he measured the amount of sky blue, the visibility, the low convective clouds means the puffy little clouds, total cloudiness, and dark paintings. In other words, because you've got cloud cover, you've got a very dark paintings. And he classified them, as you can see there, into different periods covering the Little Ice Age. So the white bars are as you come out of the medieval warm period. And as I mentioned to you, Queen Elizabeth, her reign is around 1500. So that's when the ice fares on the Thames started to freeze. And then the really cold period, the hashed or shaded lines, 1550 to 1849, and then the modern period from 1850 to 1967. Now, there's a debate about when the Little Ice Age ended or began, because it wasn't exactly the same time around the world. So one of the arguments was, they said, oh, we looked at this country and it didn't record the evidence of the Little Ice Age. Well, it was because it was delayed because of local conditions. So if you're by the ocean, or if you're in an area where the wind patterns are changing. The Little Ice Age definitely occurred. It's just a matter of when did it begin in a region and when did it end in a region. And I spent a great deal of time with Professor Hubert Lamb, who was a specialist in historical climate, talking about this. But what Neuberger showed was the different depiction of the sky conditions and then the total cloudiness. And of course, it reflects what Sven Marx had argued about, with changing cloud conditions being caused by changes in the sun, that therefore is a major factor in altering the global climate. And that was the purpose of this article. The interesting thing about this, Christian, is that it's one of the problems that we have, and it was what I was trying to work on as a scientist, was taking non-scientific measures, making them into numbers, creating numbers, and then analyzing it scientifically. So when you've got historical records, so for example, it's what we call proxy. So if you record, as the Japanese did over about 1,000 years, they recorded when did the cherry blossoms appear. Well, that depends upon the temperature and the climate. And if you see the date on which the cherry blossoms are starting to appear changing over time, that's a proxy or a reflection of climate change. It's a secondary indicator. And so when you're reconstructing climate of the past, you look for these secondary indicators of climate change. For example, at Churchill on Hudson Bay in Canada, the Hudson Bay Company recorded the date of arrival of the geese in the spring, because as the geese migrate from the warm climate up into Hudson Bay, the goose hunt was very important to them and the local people, because they would catch or shoot the geese, and then they would put them in barrels, salt them down. That was their food supply for the following winter. So they were very... The first day they saw a goose, it was entered in their journals. So I recorded that date, and then as that date changed over time, as the global climate changed and as the wind patterns changed, so it's a secondary indicator. Well, that's what Neuberger is doing here with the cloud cover. It's a secondary indicator of climate change, but it also is confirmation of what Sven Marx had argued about what causes the cloud cover to change.
Yes.
And so okay. So you can see the very dramatically different cross shading like that of the Little Ice Age period.
This is a fascinating and amazing explanation, and I thank you so much. There is an old myth, maybe of some American Indian origin, however I'm not sure, which tell us about a so-called photon belt coming from deep space, and we should already feel some changes in the solar system by the year 2012. And we are now in 2015, and I don't feel any changes, except for some microwave radiation at high altitude affecting the astronauts and airplanes travelers after many hours of flight, which had been detected earlier in December 2014.
Okay, we have to remember that we're one small planet on one very small star in a massive universe. And all of the energies and forces throughout the universe affect everything. So we talked about the cosmic radiation. Einstein, for example, believed that there was no such thing as coincidence. People say, oh, what a coincidence. Einstein said our brains could detect waves and energies that we weren't even aware of. It's somewhat like the idea that some animals can detect earthquakes before they occur, because they are able to sense changes in the gases in the atmosphere as the pressure of the earthquake builds up. So what the cosmic theory is an example of an energy. One of the ideas about how everything affects us, the sun is not only putting out heat and light, what we call insolation, that is incoming solar radiation, but it is also putting out cosmic wave energies, okay, that impact the Earth, the solar wind. Because you have to think about the sun is a nuclear bomb. It's a nuclear reaction. And like any nuclear bomb, it puts out particles, alpha, beta, gamma particles, some of which are very harmful to humans, but it's also putting out other energies as well.
I was referring to the fact that in 2012 this was part of a doomsday scenario.
No, well, but of course, you see, that's in today's world where people are trying to make money off of scaring other people to death. So, you know, if you come out and say, well, the Earth's going to come to an end, and if you want to learn about it, buy my book, and I make $1 million, and thank you very much. I mean, there was one back in the 1970s, I believe it was, called the Jupiter effect. The Jupiter effect it was part of, as the planets orbit around the sun, at certain points, the planets line up, and it was called the Age of Aquarius, and you might know that term. Well, in the Age of Aquarius, 5 of the major planets were all lined up in a line off to the southeast, and the argument was that that would then reinforce their gravitational pull on the crust of the Earth, right? And it would therefore trigger a massive earthquake. It would trigger a massive earthquake, particularly the San Andreas Fault in California. So a fellow sold a book, John Gribben sold a book called The Jupiter Effect, and he was on television and he made millions of dollars. And of course, it never came true. And he had to come out and admit that he was wrong. There have been hundreds of these kinds of alarmist claims. Oh, the world's going to end and this is going to happen. But it's just simply people exploiting human fears. And the 2012 one. But here's the problem. There were changes going on. You mentioned about the effects on astronauts and the impact. And that's what I was talking about. That one of the things that the sun is putting out the solar wind. This is particles coming into our Earth's field. As they hit the Earth's magnetic field, they are trapped and they're funneled along the magnetic lines of force, and those particles collide in the upper atmosphere, and I'm talking now 80 to 400 kilometers above the surface of the Earth. Those particles collide and they give off static electricity. So it's just like if you rub and create friction and you create electricity, that electricity causes gases in the atmosphere, particularly oxygen and nitrogen, causes those gases to glow. That glow is visible as the aurora. Okay, so just as we knew that the sunspot numbers changed and the cloud cover, later we discovered the cloud cover changed, we also knew that the the amount of aurora that was witnessed changed. So if you go back and look at that little ice age or the sunspot numbers, during the little ice age, there were virtually no sunspots. And of course, that relates to the cloud cover, but also there was no aurora seen. And Halley, the great astronomer, Edmund Halley of the Halley's Comet, he was the first one to identify the comet. He lived 70 years, and for almost all his life, there were no aurora or northern lights seen. And it's one of those great coincidences in history. He knew about the aurora. He knew about the sunspots because he'd read Galileo and all the other scientific literature, but he'd never witnessed them. And when he was, I believe he was 68 at the time, there were reports of the aurora being seen again, because you're coming to the end of the Little Ice Age, right? 1750, 1760. So the Royal Society asked him to travel up to Scotland and report on these aurora. And he wrote an article published in the Transactions of the Royal Society of Science in England, in which he starts out by saying, "I thank God for letting me live long enough to witness these marvelous phenomena." And he reported on the aurora, what he saw, and so on. And so a secondary indicator of changes in the sun are changes in the aurora. Now, to put that in modern context, the North American Indians and the Eskimos and the Indians of northern Canada, they used the aurora to forecast the weather. So they had, from long-term observation, as you know, farmers, folklore, people say, oh, well, when you see certain clouds, or one of the things my father always talked about, said, if you see the backs of the leaves on the trees, it means it's going to rain. Okay? You have all of this weather folklore, and it's all across Europe, you see it. And so amongst the Aboriginal people, the Indians of northern North America, they would watch the aurora and then make weather forecasts based on it. And of course, what amused me about that was when I talked to the scientists at Environment Canada, which is our national weather office, and said, look, the aurora are an indicator of changing weather patterns. Oh, they said, that's absolute nonsense. Got nothing to do with the weather at all. Well, it turns out that the Indians were actually correct because, of course, they had done what we call empirical science. That is that you see patterns and you watch the patterns and you see the relationships. And as you know, Christian, the whole key to science is the ability to predict. If you cannot predict, your science is wrong. And that's one of the problems we've got going on now, that all of the predictions, such as that one you just mentioned, turned out to be wrong. Well, that means your science is wrong. Well, the United Nations weather predictions starting in 1990, every single one's been wrong. Yet they're still trying to tell the people that their models work and they know what's going on. Well, the Indians of North America knew differently. And so the aurora is an indication of changes in the sun, which then reflects a change in the upper magnetic field. And by the way, that's another big issue in today's world, is how does the Earth's magnetism affect the weather? What are the relationships? And one of the things we know is that a major influence on the Earth's magnetic field is the moon. And what are the folklores about, oh, well, you know, you get a full moon at harvest time, all of those things all relating to the mechanics of weather. But of course, we're so modern, in our modern world, we're so arrogant about, we think we're so much cleverer than anybody that went before us. And therefore we don't listen to anything they tell us. So there's some fascinating stories about the sun, cosmic radiation, and the Earth's magnetic field.
Another interesting topic from your website is related to water cycle in nature. Please explain us step by step what happens when the raindrop leaves the cloud, and please explain what is a good soaking rain.
Okay, the term a good soaking rain is what my father used to talk about, because what he wanted was a rain that was going to be not very heavy and causing all the soil to wash away, but just a rain that arrived at a steady rate, because if the rain comes too quickly, it hits the surface, the ground, the soil can't absorb the rain quickly enough. And so the water forms on the surface, which then is almost like concrete. So that if you got a surface of water, a raindrop hitting it, it can't go into the ground, so it runs off, and you get overland flow of water. Now, you can see that in very heavy rainfalls out in a field, that the water runs off into the ditches. It's not absorbed into the ground. Some of that rainfall will go to evaporation immediately. So the energy from the sun is heated the surface, and the heat in the surface causes some of that water to evaporate right back into the atmosphere. But some of it moves down through the soil, and we call that infiltration, soil infiltration. So it creates a layer of about 15 centimeters of soil moisture. And that moisture is what most plants grow in, okay? And if you look at a tree, for example, you think, oh, well, it's got very deep roots. A tree has got one root called the tap root, which anchors the tree, but most of the roots spread out around the tree. And what happens when the rain falls on the tree is that it's moved by the leaves, it's shed to the outside and falls around the outside of the tree, which is where all the roots are that take up the moisture. That's why you can stand under a tree for quite some time, before the rain starts to come through the tree and you get wet. Well, if the rain comes through the tree and you get wet, then that's what my father would call a good soaking rain. Okay, so the way that the rain arrives, what happens to it at the surface is very important in terms of the plant growth and also in terms of how much of the water runs off to fill up the streams and the lakes and the rivers. And so for my father, a good soaking rain was one that recharged, filled up the soil moisture with moisture, so he knew then that his crops were going to grow. Now, the plant can take that soil moisture out. So you've got all the little particles of the soil, and in between those particles, there is moisture. The plant, through its roots, can take that moisture out into the plant, and then it moves up through the plant and into the leaves, and sunlight and photosynthesis, and the plant grows. But if you have a drought, there's a point at which there may be a minute amount of water still in the soil. There's always water in the soil, but the plant is not able to take it. And at that point, your plant starts to wilt. It starts to get weaken, and you'll see it flopping over, and because the water in it has been taken out. And that wilting point is visible, but what it indicates is that all of the moisture in the soil that a plant could take is gone. So you either have to replace that moisture in order to get the plant to grow again. Now, you can take that soil, and each particle still has a little film of water around it, but the plant doesn't have the strength in its roots to extract that. But if you put that soil into a furnace and raise it up to 300-400 degrees, you can remove that moisture and have completely dry soil, but that never occurs in nature. And so what happens to the rain when it falls, how quickly it fills up the soil moisture, how much of it runs into the river, are all part of the whole water cycle. Now, one of the things that you'll see, and your listeners can watch, is in the cities, we cover the surface, especially in the downtown area. You put asphalt and concrete. In other words, the rain can't get in, and it runs off into the storms, into the sewers and the storm systems, and is run away from the city. The problem with that is that increases flooding, and we've got examples of it all around the world. Because if you've got a drain or an area of agricultural natural land, water falls on that land, and let's say that you have a rainfall, it normally takes 3 to 4 weeks for a water that falls on the land to get into the stream. But once you start building land and building cities, the water now gets into the stream in 3 to 4 hours. So what happens is, if you plot the flow in the stream after a particular rain event, so you've got time across the bottom and rate of flow in the stream, as the rain falls, the stream flow increases. Now, under natural conditions, as with grass and forests, the peak of the runoff from that storm will be about 3 to 4 weeks after the storm. Now, in urban areas, the peak will be in about 3 hours. And so you get cities like London, England, where they've actually had to build dams in their storm system and build ponds to hold the water because it was getting to the river too quickly and causing flooding. That's happening in most cities across the world. And that's all related to this water cycle.
There is something very interesting in figure 1. It seems that it rains a lot, but the most of this rain is not touching the earth. It evaporates while falling.
Yes. Okay. Remember last time we talked about that the Earth is heated from, or the atmosphere is heated from the Earth up. So the hottest temperatures are at the surface. And the rain is forming because it's cooling up in the atmosphere. Water droplets are formed. They get together. Rain starts to fall from the cloud. And in many parts of the world in the summertime, the air near the ground is so warm that the water is re-evaporated in the atmosphere.
Amazing.
Okay? It's amazing.
Yes.
So yeah, you can see that in that diagram. That's a picture I took in Alberta in Canada. And you can see the rain starting to fall and it doesn't reach the surface. And the name that's given to that type of rainfall is called virga.
Oh yes, I understand that now.
Okay?
This is a phenomenon.
Natural phenomenon named virga. Yes. Yes. Now, if you look down at the bottom, figure 2,
Yes.
okay, what that shows you is a cross-section through the soil of the Earth. And by the way, a resource that very few people talk about, but is absolutely critical, is the soil. If you don't have soil, you can't have vegetation, okay? And the process of soil formation, so if you look at parts of Northern Europe, Scandinavia, most of Canada, there's very little soil because of the glaciers scraped off all the soil. But the rock gradually breaks down. So if you look at the bottom of figure 2, you can see the bedrock, right, which is what we call, that's called the parent material. And then immediately above it, these little chunks, that's where the bedrock is being broken down by frost action and by chemical action. So the rock is being broken up by natural processes. Then those chunks like that, which can vary in size from boulders to pebbles, to sand, to silt, and to clay, which is the smallest particle the rock will break down into. So from that broken soil right at the rock surface, and if you dig down in many parts of Romania, as you get down through the soil and you get close to the bedrock, you'll find those little particles of rock like that, okay? Gardeners in many areas will know about that. Then above that, right up to where the plants are growing in the topsoil, that's what we've been talking about. You see the roots of the plants going down into the soil moisture zone, okay? Then, as that water in the soil moisture zone, it also moves down through the soil, and the blue line marks the top of what we call the water table. So that in the rock, there is water. And so if you dig down and dig a well, then the well will fill up with water, and the water level in the well is marked by that water table. Okay? So now if you pump water out of that well too quickly, the water table in the well will go down. But if you leave it alone for a while, the water moves in from the sides of the well and the well fills up again. Okay? So that water table then, you find a water table everywhere. It's not level. I've shown it level in that diagram, but it's not level. You can have the water table at different levels depending on the rock conditions, the soil conditions, and so on. And some places, I don't know if there's anything like this in Romania, but certainly in parts of the Alps in Italy, for example, where you get a slope like this, the water table comes to the slope, and you'll get a line of springs where the water is emerging and flowing down. Okay, and so that's where the water table comes to the surface. Now, if that water table moves up to the surface, then you've got flooding. And in fact, all of the lake is if you dig into that water table, then a lake forms. So a lake is simply the water table at the surface.
But could this be what you had just described? Could this be the principle for finding underground water and build a well?
Yes, exactly.
So they first do a geological study to analyze the soil and then see if there is a chance to get water from there.
Yes, exactly. And of course, but what's important with a well is not necessarily that you can dig down and find the water. What's important is how fast the water moves through the rock to fill the well back up again. Because if you pump the water out of the well too quickly, the whole thing fails. And you'll see the water table all around the well dropping, and eventually the wells dry up. This is one of the problems in North Africa. These areas of water under the ground are called aquifers. It's a Latin term, and it's where these very large, and you hear people talking about lakes of water under the ground. Well, that's really what they're talking about. Some of the largest aquifers in the world, that is, large lakes within the soil, are under the Sahara Desert. The problem is that water was put there 10,000 years ago during what we've already talked about, during the last ice age. So when Scandinavia and Siberia were covered with big ice sheets, the Sahara Desert had a lot of rainfall, and there was lakes and vegetation and so on, and all of that water went in and was stored underground. If you pump that water out, it's not replaced, because we're now in totally different climatic conditions in the Sahara Desert. And I follow this story, but Gaddafi, who was, of course, the Libyan dictator, he started drilling wells in the desert of the Sahara and putting in huge pumps, 300 horsepower pumps, pumping water out. And he said, we're going to make the desert bloom. And one of the reporters said to him, look, you're pumping the water out so fast that in 30 years, the water will be all gone. And Gaddafi said, so will I. In other words, that's not my political problem. And of course, that's one of the things we're talking about on this program, Christian, is if you don't understand nature and how it works, you can do things that can do permanent damage, that you prevent nature's cycles working and recovering. And so that's really what we're talking about here.
Let me change the tape, and I thank you for part 3 of our very long interview.
Thank you.